Hello everyone, I am Dharmendra Kumar Chaudhary, Assistant Professor in Textile Chemistry Department at MLVTC Bhilwara. In today's lecture we will study about disperse dyeing. Before starting today's lecture, we just summarize what was studied in the last lecture. In last lecture we had studied about the role of glass transition temperature in disperse dyeing, activation energy required for dyeing of man-made fiber with disperse dyeing, role of crystallinity, orientations and heat setting in the dyeing of polyester fabric with disperse dyeing, and very basic property of the disperse dyeing as well as polyester fiber and dyed fiber. Now, as we discussed in the last lecture, very short about the basic concept involved in disperse dyeing, various steps of disperse dyeing on polyester fiber. Today we will discuss about the mechanism involved in disperse dyeing of polyester fabric, some in detail. Disperse dye on polyester fiber or man-made fiber follow the solid solution theory, where a solid dye is solubilized in another solid fiber phase. There is no chemical bonds, only physical interactions are involved, that is hydrogen bond and van der Waals force of attractions, except reactive disperse dye with nylon. In solid solution theory, as you know, in solid solution theory, solid dye is directly solubilized on another solid surface, that is fiber. That's why we call solid solution theory, which was exactly in disperse dyeing on polyester fabric process. In disperse dye bath, a very little part of dye is remain in completely soluble form and rest is finely dispersed in soluble form. It means when you start the dyeing, dye bath contain a very little amount of dispersed dye which is water soluble, and the rest is finely dispersed but water insoluble dyes. So when fiber or fabric is entered in the dye bath, the dissolved dye molecules slide past narrow pore present in fiber and get attached with physical force, causing reduction in share of dissolved dye in bath, which force dispersed insoluble dye particle to break up and go into the solution to maintain share of soluble dye in bath. It means when fabric is entered in dye bath, it take up dissolved dispersed dye on its surface, and simultaneously insoluble and finely dispersed dye in dye bath will convert into soluble form. As dispersed dye is hydrophobic in nature, soluble dye tries to be separated out from the bath and are attached by hydrophobic man-made fiber. Water acts as a vehicle for transferring the dye from bath to fiber. It means, as just we discussed, when completely soluble dye of dye bath is taken up by the fiber, simultaneously dispersed insoluble dye convert into soluble form, then it's separated out from the bath and attached to man-made fiber surface through water as a vehicle. Rate determining steps. In disperse dyeing, the effect of temperature and dispersing agent on dyeing rate is called rate determining step. It means how much amount of dye will be taken up by the fiber is depend on effect of temperature and amount of dispersing agent which is added in dispersed dye bath. Dispersing agent generally facilitate the solubilization of dispersed dye in dye bath. Now, there is a equilibrium conditions. Equilibrium conditions means after certain time there is a point. After that point there is no dyeing is happen. It means there is the amount of dye taken up by the fiber is not increased. At equilibrium condition in dispersed dyeing is when rate of dissolution, rate of surface deposition rate of absorption, diffusion of dye becomes equals to each other. It means there is no further dyes. As we discussed in last lecture, various steps of dispersed dye, that is, first dissolution of dispersed dye, then surface deposition, then absorption, then finally diffusion of dye inside the fiber structure. So when the amount of dye taken up the fiber is not increased, at that situation we call equilibrium condition. So in very short, at equilibrium conditions, rate of dissolution, surface deposition, absorption and diffusions of dye become equal to each other. Now we will discuss about the role of carriers in dispersed dyeing. As you know, dispersed dyeing is done by three methods in general, using carrier, high temperature, high pressure or thermosol process. So in all type of dispersed dyeing, we add dispersing agent very first. So dispersing agent is inherently present in any type of dispersed dye. So dispersed dye is insoluble in water, but little solubility is achieved at high temperature. In dispersed dyeing, dye molecules should remain in dispersion state, not in clustered form. To keep them in desired state, dispersing agent is added in dye bath along with increasing in temperature. So when we add dispersing agent in dye bath, then solubility of dispersed dye is increased, but simultaneously by increasing the temperature of dye bath, also solubility increase. Dispersing agent impose negative charge on dye to improve aqueous solubility, and due to this, repulsion among dye molecules increase, and data potential is minus 30 MV to 80 MV. If we add dispersing agent in excess quantity, then exhaustion of dispersed dye is reduced and develop poor rubbing fastness. Now we can say, if we add dispersing agent in excess quantity, then it will negatively impact the dyeing of polyester fabrics. Dispersion of dye is achieved through interaction between dye and dispersing agent. So quantity of dispersing agent is depend on amount of dye and do not have any relationship with MLR ratio. It means how much amount should be added in dispersing agent in dye bath is exactly depend on how much amount of dye you will taken, and very specifically the amount of dispersing agent is varied with structure of dye molecules. Again, one of the prerequisite of dispersing agent is that the cloud point of dispersing agent should be at least 5 to 10 degree higher than dyeing temperature. If temperature is not more than 5 to 10 degree higher, then there is chances of precipitation formations of the dye during dyeing. So to avoid the precipitation formation, dispersing agent must have cloud point at higher than 5 to 10 degree centigrade of dyeing temperatures. Dispersing agents belongs to mainly formaldehyde condensate, fatty alcohol ethylene oxide condensate and lignin sulfonates types. Along with dispersing agent, we use leveling agent in dispersed dyeing. Leveling agents promote uniform distribution of dye throughout the fiber structure by reducing the strike rates. Leveling agents should have cloud point beyond the dyeing temperature, as same we discussed in discuss for dispersing agent, that the cloud point should be higher than the dyeing temperature. Leveling agents are generally non-ionic in nature, ethylene oxide condensate with aqueous solubility below cloud points, and they increases or enhance the solubility of dyes and excess use reduce dye uptake. If you use leveling agent in excess quantity, then they may be work as a retarding agent. It means excess use of leveling agent decrease the dye uptake. Now, very third important component of the disperse dyeing is carrier. If you choose low temperature dyeing of polyester fabric. Functions of carriers.